Hey guys, welcome back. Let's talk about some more topics for the laws of thermodynamics. So we're going to be looking at calorimetry and the standard enthalpy of formation and reaction. This is a review from chapter 6, and it wasn't something we actually covered in 110, so we're talking about it now. And then we're going to talk about section 8 from chapter 11, which talks about phase changes. Okay, so these are what we're going to be covering. Let's get into that. Questions, comments, problems before we do. If you do, think you know how to reach me, email, phone, WebEx, you name it. I'm here, I'm available, I will meet with you anytime. Well, mostly anytime. So let's talk about calorimetry. Now, calorimetry is a way that we can study the amount of energy that is required to do a particular process. So we can look at heats of reactions, we can look at heat changes from solid to liquid, lots of different things. In order for us to be able to do that, we have to be able to talk about this calorimeter that's here. And of course, this is very, very hard to see at this point. So let's see if we can zoom in a little bit. Hopefully I can move that over. I can't. That sucks. Cheat. Give me a second. There's more than one way to skin this cat. I swear it's. I'm going to go into Zoom because I can't see. I swear there's one way to do this. I don't understand why I have to be so stubborn. I'm sorry. I know this is kind of silly. Anyway, let me take you to, instead of doing this, let me take you somewhere smarter. So I'm logging into Alex. I'm going to go into your shell. I'm going to look at your textbook. Find a calendar there. And textbook. Okay. So this is actually the image that I was looking for. And what you'll see is that there's a thermometer. There are ignition wires here to be able to apply the energy to this. This is a stirrer. This is a water bath that's on the outside of this thing we call the bomb. So this is a bomb calorimeter. So there's a closed container in the inside that we can do a reaction in. And we apply energy to start that reaction, and then we can look at how much the temperature of the water changes as a result of what happened inside of that container. In order to be able to do that, we have to know some things about the calorimeter, how much energy that calorimeter will accept on its own, how much energy the water can accept on its own, so some things like that. And that can give us information about what is happening in that bomb. Okay. Now, what we talk about is we can calculate the heat value for the calorimeter by looking at the C for the calorimeter. Okay, the quantity C-cal is calibrated by burning a substance with an accurately known heat of combustion. So if we know what the heat of combustion is, and we know what the change in temperature is for this particular thing. It allows us to calculate that C-cal. Okay, so then we know that there's a constant for the calorimeter, which is C-cal, which we can then use moving forward. This is done before you buy a bomb calorimeter so that they come calibrated. Okay, that's one portion of this. One other thing that we often talk about is taking something that has a specific heat in it. So a lead pellet having a mass of 26 point. No, hold on. Let me go back and see if I'm missing things. I hate it when I do this. Skip around a little too much. So we know that C, okay, so the amount of heat capacity, how much that thing can take except as heat, is given by the mass times the S. Okay. S is the specific heat of that material. Okay, so that the specific heat, how much it can accept, has a lot to do with how much heat it can take. We also know that the Q, that heat transfer, is equal to C times delta T, which therefore is equal to M times S times delta T, where M is the mass, S is the specific heat, and delta T is the change in temperature. So delta T, T final minus T initial. And it's always T final minus T initial. Remember that they need to say that way because it's important for the signage. When we do heat of combustion reactions, they can be measured in a machine like the one above. It's called the bomb calorimeter, which I actually mentioned. It's a closed system, constant volume. The change in heat, Q system, is an indicator of the energy of the reaction. So Q reaction is equal to the Q for the system plus the Q for the calorimeter plus the Q for the reaction. So if we know the Q for the calorimeter and we can measure the Q for the system, then we can find the Q for the reaction. Q-cal is the specific heat capacity of the calorimeter, which can be measured experimentally using Q-cal equals C-cal times delta T, or C-cal is equal to Q-cal over delta T. We use a material with a known heat, like benzoic acid, and measure the temperature change and solve for K-cal. Okay. In this particular case, the K-cal that they had for this particular calorimeter was 5.654 kilojoules per degree C. It's a measure of delta U, not delta H. Okay, so this is for delta U and not just the heat. Okay. Now, if it's constant pressure calorimetry, it can be used to measure the heat of reaction from non-combustion reactions. Okay, so since there is constant pressure, the Q reaction equals delta H. Okay, remember, in this case, it did not, and that's because when we do combustion, we generate gases that weren't present initially. So that can't be just from the heat. Okay, there's work involved there, and therefore we have to look at that. All right. But in this case, if we're talking about constant pressure, then that Q reaction equals delta H. Q-cal equals 0 for the calorimeter. It's really small, so we're going to ignore it. And these are actually just styrofoam cups that are put inside of each other. And there's a thermometer through it and a stirrer in there, and we look at the reaction mixture that goes on. So the specific heat capacity of an added component can be determined. So there's a method in example 6.7. And an example of heat of reaction can be determined using a method similar to example 6.8. Now, 6.7 is this thing right here. So from your textbook, it says a lead pellet having a mass of 26.47 grams and 89.98 degrees C was placed at a constant pressure calorimeter of negligible heat capacity containing 100 milliliters of water. The water temperature rose from 22.5 degrees C to 23.17 degrees C. What's the specific heat of the lead pellet? Okay. So I have this lead pellet, it has this mass, it has this temperature, and then there's 100 grams of water that starts at 22.5 degrees C, and eventually we get to 23.17 degrees C. So we know the mass of the water and the lead pellet, as well as the initial and final temperatures. Assuming no heat is lost to the surroundings, we can equate the heat lost by the lead pellet to the heat gained by the water. Okay, so the Q for the PB plus the Q for the H2O is 0 because we didn't lose anything. So QPB is equal to the negative the QH2O. The heat gained by the water is given by QH2O is equal to the mass times the specific heat times the change in temperature. That's that QH2O ms delta T, okay? Where M and S are the mass and specific heat, and delta T is T final minus T initial. Therefore, QH2O is equal to 100 grams times 4.184 joules per gram degree C. That's specific heat of water. There are some specific heats, just so you know, that are listed in the exam handouts. I'm trying to remember which page they're on. But there are a few in here. Where did I put them? Oh, it's on the bottom of page 7. It says specific heat capacities, grams per degree C at STP. And there's aluminum, copper, gold, iron, lead, nickel, silver, tin, zinc, and water are all listed in that table. So just so you know. This is our specific heat, and then our final is 23.17 degrees C, and our initial was 22.50. So that gives us a Q for the H2O of 280.3 joules. Okay, notice that's in joules. Because the heat lost by the lead pellet is equal to the heat gained by the water, QPB is equal to negative 280.3. So same value, different sign. Solving for the specific heat of PB, we can do that, and we find that that specific heat is 0.158 according to our calculation that we've done here. Okay, so that's an example of how we do this with a solid. Right. We also talk about doing this in example 6.8 for a reaction. It says a quantity of 100 milliliters of 0.5 molar HCl was mixed with 100 milliliters of 0.5 molar NaOH in a constant pressure calorimeter of negligible heat capacity. The initial temperature of the HCl and NaOH solutions were the same, 22.5 degrees C. I'm assuming that's room temperature. And the final temperature of the mixed solution was 25.86 degrees C. Calculate the heat change for the neutralization reaction on a molar basis. So we assume that the densities and specific heats of the solutions are the same as they are for water. So we're assuming 1 gram as our density and 4.184 joules per gram degree C for the NaOH and HCl. Now, is that true with an experimental error? Yes. Okay, we can do that. So because the temperature rose, the neutralization reaction is exothermic. How do we calculate the heat absorbed by the combined solution? What is the heat of the reaction? What is the conversion factor for expressing the heat of reaction on a molar basis? So, assuming no heat is lost to the surroundings is equal to the Q of the solution plus the Q of the reaction. Okay, so our solution plus our reaction, and that's equal to 0. So the Q of the reaction is equal to the negative Q of the solution, where Q of the solution is the heat absorbed by the combined solution. Because the density of the solution is 1 gram per milliliter, the mass of 100 milliliter solution is 100 grams. Thus, Q for the solution equals the mass times the specific heat times the delta T. So 100 grams plus 100 grams, because we had 100 in there, 100 from each one, so that's 200 grams total, times 4.184 joules per gram degree C, times the difference, 25.86 minus 22.50. And that gives me 2.81 times 10 to the third joules, or 2.81 kilojoules. So that is the heat of reaction for what we looked at. From the molarities given, the number of moles of both HCl and NaOH is 1.0 times 10 in that solution. The 1.00 times 10 to the second molar solution is 0.5 over 1 liter times the 0.1 equals 0.05 moles. That's how many moles I have. So I took the molarity times the volume, that gives me the number of moles. So that's how many moles I have. Therefore, the heat of neutralization when 1 mole of HCl reacts with 1 mole of NaOH my heat is negative 2.81 kilojoules divided by the number of moles that were present, the 0.050, and that gives me negative 56.2 kilojoules per mole. That's awesome. Okay, so we can use those pieces of information to do calculations. Now, is this something that you're probably going to have to do? Yeah, at least on the lab final. So that is something that you will see on the lab final. There are questions in the lecture final that are based on this as well, because it was something that was supposed to be done in the lab. There is a calorimetry experiment in ALEX that you can look at that has some calculations with it. There is also a walkthrough of the calorimetry experiment that we would have done in the laboratory. So you can take a look at that as well. And all of those calculations are laid out for you in the Excel spreadsheet that's included on D2L. So you can look at both of those. Okay? You are not expected to do anything with them, but you can look at them so that you can see what kind of math you might be asked to do. Okay? Questions, comments, problems there. Cool. Awesome. And if you do, please let me know. Now, this is that 2.7, so I went through that example there. I also went through the other one. So am I where? Yes. Okay, so we're going to take a break here so that we can transition to heat of formation in just a few minutes. We've actually talked about this sort of kind of without saying what it was. So we'll get back to that in just a few minutes. I will see you guys soon. Thanks.